Hello, in this video we're looking to derive the equations necessary to code for the height of a non-circular pipe. And so to begin, we have our diagram drawn here. So we have two views of our non-circular pipe labeled with the different positions. So this is position 2 and position 1. So we have the pressure at position 2 and the pressure at position 1. And the pressures at these different positions are actually equal. So P1 equals P2, and then we have it labeled as the change in position delta z, and then the change in position delta x, and then we have the angle theta. Over here we have the width of the non-circular pipe and then the height of the fluid. So we're given the width is 0.5 meters, we're given the flow rate is 1 meters cubed per second, and then the angle is a 15-degree incline. And so what we're looking for is the height. And so the first thing we want to do is we're going to start with Bernoulli's equation. So the pressure at position 2 minus the pressure at position 1 divided by the density plus the gravitational acceleration times the position 2 minus the position 1 is equal to, so we can actually, normally it would be a negative frictional heating, but we, in a previous video, defined that as 4 times the friction factor times the change in position divided by the diameter times the velocity squared divided by 2. And so what we can do is we can actually divide across by, well, first let's define what the position 2 minus position 1 is. This is just going to be the change in position z, and the change in position z can be defined as the change in position x times sine theta, because if you look here and the angle of theta, that works out. And so if we plug this in for here, so we have pressure at position 2 minus pressure at position 1 divided by the density plus g, gravitational acceleration times the change in position z, is equal to 4 times the friction factor times the change in position x divided by diameter times the velocity squared divided by 2. What we can do is we can start simplifying this. And so the 4 and the 2 will cancel, leaving a 2 in the numerator. And then we can actually divide across by, well, let's plug in for delta z. So that's going to give us delta x sine theta equals 2 times the friction factor. And then so what we can do is divide across by delta x and multiply it by density. So if we divide across by delta x, that will give us a delta x in the numerator here. It will cancel here and cancel here. And then we're multiplying across by the density, so we'll have a density here and a density here. And that's what we're left with for the Bernoulli's equation. So what we'll need to do is model it by a circular pipe so that we can approximate the non-circular pipe. So for a circular pipe, if we were to connect it to shear stress, we know that the density times the gravitational acceleration times the area times the change in position x can be equal to the shear stress times the wetted perimeter, which is the area on the sides, times the change in position x. And so what we can do is cancel out the change in position x and bring the area to the other side. So we have the density times the gravitational acceleration equals the shear stress times the wetted perimeter divided by the area. And so for a circular pipe, the wetted perimeter divided by the area is equal to 4 pi over, pi times diameter divided by 4 times the, pi times the diameter squared divided by 4. And so if we cancel out the pi's, cancel out one of the diameters, we're left with the wetted perimeter over area is equal to 4 divided by the diameter. And so what we can do is we can plug that in for here, as well as, so we'll have the density times the gravitational acceleration divided by is equal to the shear stress times 4 divided by the diameter. And so because the pressures at position 1 and 2 equal one another, this will cancel, this will be equal to 0. And so what we can do is we can use G as a commonality here, so we can bring the density over to the other side. So we're dividing it, so it'll be the shear stress divided by the density is times 4 divided by the diameter is equal to the gravitational acceleration. And we're going to use this equation here and plug it in for this gravitational acceleration over here. And so we'll have shear stress divided by the density times 4 divided by the diameter times sine theta is equal to 2 times, and then another thing is this density and this density actually cancel out, and so sine theta equals 2 times the friction factor times the velocity squared divided by the diameter. So now what we can do is we can isolate the shear stress over here, and so if we isolate the shear stress, we have, well, first let's start with what we'll multiply by. We'll multiply by density and diameter, and so we'll have 2 times the friction factor times the velocity squared multiplied by the diameter multiplied by the density divided by, we'll be dividing by 4 sine theta and then the density, and so the two densities will cancel out, and then the 2 and the 4 will cancel, leaving a 2 in the denominator. So we have shear stress of a circular pipe is equal to the friction factor times the velocity squared times the density divided by 2 times sine theta. And so now what we can do is, we'll use this as an approximation, plugging it back into this equation. We need the wetted perimeter divided by the area for a non-circular pipe. So that's going to be the wetted perimeter divided by the area. So if we're looking at this diagram here, the wetted perimeter is going to be 2 times the height plus the width divided by the area is going to be the height times the width. And then so what we can do now is we can plug this equation and these two expressions into this formula here. So we'll have the density times the gravitational acceleration is equal to, first we have the shear stress expression, so friction factor times velocity squared times the density divided by 2 times sine theta multiplied by, we have this wetted perimeter over area expression, so 2 times the height plus the width divided by the height times the width. And so the densities can cancel out, and so that's going to leave us with the gravitational acceleration is equal to the friction factor times the velocity squared times 2 times the height plus the width divided by 2 times sine theta times the height times the width. And so now what we can do is we have this velocity here, and we don't know what the velocity is, but we are given the flow rate. And so flow rate is just the velocity times the area. And so if we isolate the velocity, that's going to give us velocity equals flow rate divided by area. And we know, like we mentioned earlier, the area is just the height times the width, so it's going to be flow rate divided by height times the width. And so now what we can do is we can plug this in for the velocity of this equation. So that's going to give us the gravitational acceleration is equal to the friction factor times the velocity squared, and so that's going to be the flow rate squared times 2 times the height plus the width divided by, we have 2 sine theta, and then we have already a height times width here, and then we're going to combine it with another height times width squared, so that's going to give us height times width cubed. And so now the only thing that we have remaining is the diameter. And so the diameter, if we look at the two wetted perimeters of a non-circular and a circular pipe, we can actually set them equal to one another. And so because we don't have the height, and so we have this wetted perimeter over area expression, so that's going to be 2 times the height plus w plus the width divided by height times the width is equal to, and then we have 4 over the diameter. And so now what we need to do is isolate the diameter. And again, the reason we're doing this, I don't know if I clearly explained it a second ago, but it's because we're trying to find the height, so we don't have the height, and so we need to isolate it. And so when we put it into the code, we'll actually put in the diameter. And so we isolate the diameter, we'll have so we'll multiply by diameter, so we'll have 4 times the height times the width divided by 2 times the height plus the width is equal to diameter. And so another reason why we need to do this is because the friction factor is a function of Reynolds number and the roughness of the material. And so this is a code that we coded in a previous video. And so again, the Reynolds number is the density times the velocity times the diameter divided by the viscosity. And so that's another reason why we need the diameter, is so that we can plug it in for the Reynolds number, which then we'll use for the friction factor, which then we'll use for the gravitational acceleration expression. And so what we'll actually use is the root solver in Collaboratory. So it'll make a little more sense once we head over to the code, why we need all these equations, or all these expressions. But so we'll be needing this diameter expression, the Reynolds expression, and the gravitational acceleration expression. So let's head on over to the code and write it out. Okay, so now that we're in the code, hopefully this will make a little more sense as we code it out. So first here we just have imported some packs that help us with the mathematical as well as when we use the root solver. So we have imported numpy as np, and then from the pack scipy.optimize we're going to import root. And then this next one is some of the constants that we use for the Churchill friction factor. So we have mu, which is the viscosity, and then we have rho, which is the density. So that's, the viscosity is 1 times 10 to the negative 3 Pascal seconds, and then the density is 1 times 10 to the third kilograms per meters cubed, and then the gravitational acceleration is 9.81 meters per second squared. And then so this is the code that we wrote in a previous video that in the previous video explains how we get this equation. And so we just copied and pasted it from the previous code that we wrote. And so now we can actually write some new code. So first we're just going to input our givens. So we are given the width, which is 0.5 meters. We're given the flow rate, which is 1. So that's going to be meters cubed divided by seconds. And then we have the angle, so theta, which is 15 degrees. So we have to make sure it's in radians. So that's going to be multiplied by np dot pi, which is just pi 3.11415 divided by 180. And so now what we can do is we're going to be using our root solver. So what a root solver needs is it needs an equation that is a vector. And so return vector. And so we have to initialize or say what our vector is. So the first part of the vector is just going to be the height, which is what we're looking for. And so now what we need to do is start inputting the equations that we derived. So first we have that the diameter is equal to 4 times the height times the width divided by 2 times the height divided by, or plus the width. And then using the diameter, or using the, we'll also need to define the velocity, which is the flow rate divided by the height times the width. And then we have Reynolds number, which is the viscosity, so, or excuse me, the density times the velocity times the diameter divided by the viscosity, which is mu. And so now we can use the Churchill equation, which is the Reynolds number, and then the surface, which here we'll just use 1 times 10 to the -6. And so those are the equations that we derived on our whiteboard here. And so the final equation that we derived was the gravitational acceleration. So for the root solver, this is the equation that we were actually solving for the root of. And so we'll want to return this. But for root solvers, it needs to be set equal to 0. So we're just going to do the gravitational acceleration minus, and we put in our equation. So we have so this is F here. This is the friction factor. And so we'll have F times the flow rate squared times 2 times the height plus the width. So that's the numerator, and then we have that divided by 2 times sine, so we'll use np.sine theta times the height times the width to the third power, so cubed, and so should be multiplied by, and then this, because it's the root solver, will have to be an array, so we'll put brackets around it. So we'll shift enter, hopefully it all works. So now what we can do is we can do root, and it will be the equation. So that's what we have defined here. And then an initial guess, so we'll do 0.1. If we shift enter. So here we have the height is 0.14. And so that's the code. So we wrote out a bunch of equations that didn't seem to all go together, but we put into the code, we use so ultimately we're looking for the height, and so the diameter has the height in it, the velocity has the height in it, and so we use the Reynolds number to find those two numbers, and we need the Reynolds number because we have to find the friction factor, which is a function of the Reynolds number and the surface material. And then we need all of those values for the final gravitational acceleration, which when set equal to 0 can be put into the root solver, which is what we have here. And so we used all of those equations in our code to find the final height of this problem, which is 0.14.